Hello, everyone, and thank you for attending my talk on Describable Typesafe computations. So before I start with the talk, let me just introduce myself. I'm Daniel. I'm a senior consultant at InnoQ and author of 3 Scala books. So if you're interested in any of these, they are available in digital form on LeanPub, and the Scala from Scratch books are also available as print-on-demand hardcovers at Blurb. All right, so when we think about Scala, most of the companies that immediately come to mind, they are all web scale. And also the libraries and the frameworks that have pushed Scala as a language are mostly known for building highly scalable and performant applications, or for allowing to process big amounts of data efficiently. So Scala is generally known for resource efficiency and scalability. But sometimes these are quality goals that don't matter at all to the business. So sometimes what the stakeholders mostly care about is correctness or auditability. And that's mostly the case if money is involved. For example, if we ask the question, how much money do we owe this party? Or under which conditions should we lend money to that party? And in such cases, we are sometimes required to produce a detailed log of all business critical calculations. And this log allows stakeholders to understand and reproduce all the steps of our calculation. And it makes it a lot easier for them to identify bugs or also problems with the data that is fed into the calculation. And in the past few years, I have been working in multiple projects where the teams faced exactly this issue. And each of the teams had a different background and experience. So I've also seen a few different approaches at solving the same problem. And that's why in this talk, I want to compare the different approaches I've seen and also show their pros and cons. And I'm going to use an example use case for this, which is SelfPub. It's a platform for creating and selling self-published digital books. And of course, any similarities to a self-publishing platform I know are purely accidental. And there are 2 rules that are relevant for this talk. The royalty rate for a book sale is 75% of the revenue. But also SelfPub has a rule that it keeps at least 80 € of the revenue of each sold book. So keep in mind these business rules for now. Now here is a plain calculation, which is a bit simplified, because we're now ignoring the second requirement that the minimum revenue for SelfPub should be 80 euro cents for each book sale. And we will get back to that second requirement a bit later in the talk. So we get a list of sales, which is actually a list of the prices that each book was sold for. And we have a royalty rate. The total revenue is the sum of all these sales prices, and then we multiply the 2. So this is the basic implementation, which lacks the requirement that we create a calculation log for our stakeholders. Now, the first approach I'm going to introduce just uses standard logging. So in this implementation, we log all the input variables of our calculation, which is the royalty rate and the total revenue. And we also log all calculation steps. In this simple example, there's only one calculation step, which is the third log entry. And if we do this, then the log output will look something like this. All right, so what can we say about this solution or about this approach? Well, first of all, it is easy to implement. But on the other hand, it's quite difficult to read and maintain. Of course, this readability issue doesn't really become so much apparent in this simple example, but it really gets worse in bigger calculations. And there's also a complexion of calculation and logging, because we see that each calculation step is it's always followed by the logging steps, so they are interwoven. And yeah, this is part of why it's not so easy to read. But this solution is also error-prone, because we need to be careful that the logging of each calculation step is actually consistent with the actual calculation in our code. Because we might actually log something different. Maybe we actually multiply the total revenue with a number of with a royalty rate, but we say in our log that we do something different for some reason. And also, using this approach, it's a bit difficult to make the calculation log available to our stakeholders in an easy way. In the first project where we used this approach, we used a variation where we actually didn't log using the standard logger, but we logged into an in-memory data structure instead, which then could be persisted to a file and downloaded by stakeholders. And the last point is logging as a side effect. That's not such a great thing. So if you imagine that this simple royalty calculation is just part of a bigger calculation, where maybe this royalty calculation is used in multiple other calculation steps, then it makes a difference for the log output if we only call this royalty calculation method once and then use that result value multiple times, or whether we call the method multiple times. And that can be quite confusing, of course. So all in all, I can't really recommend this approach to creating an audit log or calculation log for stakeholders. So, as I said, in one team, they used this approach first, at least. They were not very happy for the reasons I mentioned. And in a completely different project, another team had a similar problem, and they used a library called treelog instead. So even if you never use treelog, it's definitely worth looking at the README of this project just for the beautiful language alone of the project description. Treelog is a functional Scala library by Lance and Channing Walton. It's available on GitHub, and according to the authors, it's a veritable complex of computation and description in perfect harmony. And they continue describing how this is achieved. Treelog achieves this remarkable feat with a writer monad writing to a tree representing the hierarchical log of computation. Treelog is based on cats, or optionally on Scala Z if you prefer that. And it's quite innovative because it introduces this concept of a described computation. I'm not going to explain in detail how treelog works, but I'm just going to show you here the three most important types of the library, which are all actually type aliases. So as you can see from these type aliases, treelog uses a monad transformer, which is either T, and the writer monad, which is writing into a tree structure, the log tree. So if we use treelog to create our computation of the royalties together with a log, then it will look like this. Our return type is now not a plain big decimal anymore, but a described computation of big decimal. And because of the monad transformer and the writer monad, we're using a for comprehension to describe our calculation. So here each calculation step or input variable can be annotated with a label. And that label is what you see after the tilde arrow. And to provide an annotation, you need to provide an annotation function which actually receives the result of the annotated calculation step. And then it can make use of that result to create the annotation. For example, here we use the rate, or in the last step, we actually put the ref share into our description of this calculation step. So if you want to actually get the result of a described calculation, then we can do it like this. We have a described calculation in our royalties field, and first we need to access the writer monad from the either t. That is the first dot value. And then we can access the actual value with a second dot value. And it's an either of string or big decimal, because a calculation can fail. Think, for example, of a division by 0 or some missing input value that is actually required. And we can show the tree log, which is the log of our calculation. So we can access it using the written method of the writer, and then there is an instance of cat's show type class for this. So we can get a string representation of the calculation log. And that string representation of this calculation log also has a tree structure, which we can see in this slide. And the difference to a flat log output might not be that big in this short example, but if you have a few more calculation steps in a somewhat more realistic calculation, then this can make a big difference. So what's the assessment? Well, first, this concept of a described computation, which is a hierarchical log with a tree structure, that's a really great idea, in my opinion. Now, about this cats or Scala Z dependency, I'm a bit conflicted. So if you already use cats, it might not hurt you to introduce this library. But on the other hand, dependency hell of version conflicts is often closer than you think. And then there is this whole monadic API, which uses monad transformers, which is definitely an elegant implementation, but it can be an obstacle in less experienced teams. And while this is all more readable than this traditional log-based approach I've showed as a first solution, it's still a bit verbose and also error-prone, because we still need to annotate steps manually. And here it can still happen that the annotation of a calculation step says something different from what we actually calculate. But on the other hand, on the pro side, a described computation is referentially transparent. So it doesn't really matter how often you call a method which returns a described computation as part of a bigger computation. This tree log will always look the same. So this is pretty good. So one team was pretty happy with tree log, but in that other project where they first used this simple logging approach that I mentioned, they also looked at tree log, but they said, we only want to log our calculation steps. Why do we need a monad? So they were not really willing to introduce a monadic API just for the purpose of logging. And in addition, they also didn't have a lot of experience with the underlying concepts like monad transformers and so on. So in that project and in that team, we came up with a third approach. And the goals of this were the following. we wanted to have a familiar API. So even though it did log the calculation steps, it would look similar to plain calculations. We also wanted to have a log that can be read and understood by stakeholders. And very important, we needed guaranteed consistency between log and actual calculation. Well, this is something where the first two approaches didn't really help us. In addition, the goal was to have a reduced surface area for calculation bugs, and finally the ability to serialize the complete calculation, for example, to JSON or protobuf or some other format. So the solution that we came up with is self-describing calculations, where calculations were represented as data. And in addition, it was important that we represent different quantity types in the type system. Of course, the third point is something that you could also do in the first and the second approach. But here it was really an important aspect of the solution, because we were using type classes for all operators that support self-description, basically. And so using these type classes, we could also express which operations are possible for which types and what the result types would be. Based on what we did in that project, I created an open source library called calclog. So calclog is built on these very same principles I already mentioned. It's still kind of a proof of concept right now. But yeah, it's available on GitHub and the link on this slide. And it has two additional goals. So because it's an open source library, it should be extensible. So it has to be open for new quantity types that are not supported in the core library, but also for new operators that are not built into the library. And in addition, in contrast to treelog, it is supposed to be a zero dependency library, at least the core library. All right, so now it's time for some calclog demo, and also to show you what the calclog implementation looks like. Oops. So I'm going to switch to VS Code now. I hope you can all read this, that the code is big enough. So, as I said, in calclog, we have this goal that calculations are data. So you can see here that calculation is an enum, which has exactly 3 cases. So a calculation can either be a variable, which is just an existing value with a name, or it can be an expression, which contains an op of type A, or a binding, which basically just gives a name to an expression. All of these cases also have an additional parameter, the value formatter. This is very similar to the show type class. So it's just a way to, or basically a function for transforming a value of type A into a human readable string. The enum calculation also extends calculation description, and that is the interface that can be used by a calculation description formatter to turn this whole calculation description data into a string. We also, of course, need to be able to extract a value out of a calculation. So this is what extract value does. It returns a value of type evaluated of A. And evaluated of A is just a type alias for either string or A. That's a bit similar to what you saw in treelog. A calculation description knows how to show its value, and it allows you to access the inputs to this calculation as a sequence of calculation descriptions. Okay, you saw that expression contains an op of A, and op, on the other hand, is also an enum type with a few different cases. And this is a generic representation of operators, what you see here. So infix can represent arbitrary infix operations. Then we have one arg and two arg functions. And we can represent a literal value as a subtype of op, and also unary operations. Okay, so this is a generic representations of operations. Let's see what default operators are supported and how this is implemented. So for each operator that is supported in the library, there's a type class. For example, there is the plus of A, which is a function from two A's to an evaluated of A. We also have minus, times, divide, and so on, and square root and unary minus. So there's not that many built-in operators right now, but as I said, it's pretty much a proof of concept right now. Now we have these type classes. We also need some syntax. So this is the how we implement the syntax for all of the operators that are built into the library. So we use extension methods for calculation of A, so that we have a plus, minus, times, and so on. And these extension methods require an instance of the, in case of this plus operator, an instance of the plus type class and a value formatter. And they will turn an expression. And these are all implemented very similar. And as you can see here, we in this case, the op is an infix op, and we need to provide the symbol that will be used when this expression is turned into a string representation. Okay. And the final building block is what's in the DSL trait. So if I have an expression, I can turn it into a binding with this extension method with the backwards tilde arrow. And similarly, I can have an arbitrary value of type A. And if there is a value formatter for it, then we are able to turn this into a variable using the tilde by providing a name. Okay, let's do a simple demonstration of what actually using this DSL looks like. I have a worksheet here. I'm importing the defaults of calclog here, which gives me a lot of type class instances and extension methods. And let's say we want to calculate the parameter of a circle. So we can have a value here and use a tilde to turn this into a variable. So this is a calculation of type double, and it's a variable. It has a name and a value. And as you can see, also a value formatter, which will be used for turning this into a string. We also need a radius. Let's say this is 15. And again, we have a calculation of double. And we can have our calculation step, which is 2 times this times this. So now we have an expression of type double. And calculation can be run, which turns it into a described calculation. And a described calculation has a value of type evaluated. So because the calculation is successful, we see here a write of 94.2477 and so on. But we can also get a description of the calculation. So this is a value of type calculation description. And as you can see here, this is basically data containing, as an expression containing an infix, containing an expression, and so on. They are literal values and a few functions for the actual operations. And what we can do now with this description is we can format it. So due to this import of the defaults given, the default calculation description formatter is used. And this also creates a tree representation. So you can see here calculating ... and then we see the input variables and the result. So because we just have an expression for parameter, we see here this ... but we can also turn it into a binding. And now we see calculating parameter and got parameter. So unlike tree log, we don't actually have to create these calculation step annotations by ourselves. So instead, all we need to do is give names to variables or to bindings. And the rest, the actual calculations, the expressions, they are self-describing. So let's have a look at how we can use this for our royalties calculation. So this is a simplified royalties calculation, again, where we don't take into account yet the 80% revenue for SelfPub for each sold book. So this looks a bit similar to the plain version without logging. The only thing we add is these labels for our variables and for our calculation step here. And now we can run the calculation. I have a main method here. And this is the result. So this looks almost the same as the result of our tree log implementation using this for comprehension. But we didn't have to write any annotation for the calculation step. Okay, so let's say we want to finally satisfy the business rules of SelfPub, which is that they want to keep at least 80 € per book. So now our calculation gets a little less trivial, and we cannot express this calculation without defining our own custom operator. Because for our solution, at least the one that I came up with, I need a min function, which gets two values and returns the one that is smaller. And calclog doesn't have that built in right now. But the good thing is that it is very easy to do that. So let's see how we can do that. So here I have a custom operators trait, and in that I define my own type class, which is the minimum type class. The shape is pretty much the same as, for example, the plus type class. Here I also define instances of this type class for any type A that has a numeric instance. And finally, we have the min method, which requires a minimum and a value formatter of A. And it expects two values of type calculation A and returns a smaller one as an expression of A. And that expression contains an op that is a 2-args function, which here receives the two calculation inputs. It receives a function that knows how to actually do the calculation and a name for the function. All right, so this is our minimum operator, and let's see how we can use that. So here we have the implementation of the royalties calculation for 1 month, which actually satisfies the business requirements. So this is why there is a bit more going on now than in the simplified solution. So in addition, what we already had, we define a minimum SelfPub share per book, which is 0.8. We also calculate the minimum SelfPub share in euros, which is based on this minimum share per book and the number of sales. And at the end, we return the minimum of the calculated revenue share and the maximum royalties in euros. So this maximum royalties is the total revenue minus the minimum SelfPub share in euros. So let's actually run this calculation. So we're giving it, again, some example input data, and then we print the formatted calculation description. So as you can see now, the difference is a bit bigger between just doing the plain flat logging and having a calculation tree. And also now maybe you can see a bit more that it pays off, that we don't have to annotate each calculation step manually. So here is the complete calculation log as a nested tree structure. At the end, it shows the result. Royalties is min revenue of revenue share in euros and maximum royalties in euros, and that is the result. So let's go to the implementation again. It was just this, basically. Okay. But I also said that we wanted to have type-safe calculations. And right now, all we did is use big decimal everywhere. Now, of course, it's easy to get things wrong when all of your types are big decimals. So we introduce some safer types. We have a type euros, which is an opaque type based on big decimal. It has an extension method called value, which extracts a big decimal. I also have a convenience method, extension method for a list of euros, which gives you the total amount of euros. And we also have a type royalty rate, which is also an opaque type of type int. And we validate that it's a value between 0 and 100. And we have an extension method that turns it into a fraction between 0 and 1. Okay, but these types, royalty rate and euros, they are unaware of the calclog library, which is good. But we can tell calclog how to format these values and also what operators are allowed by defining appropriate type class instances. So let's do that here. First, we have two value formatters, one for euros and one for royalty rate, where we implement the format method to have a nicer representation of values of these types. And below that, we have a few operator type classes. So we say that yours can be added. We say that it can be subtracted. And we also can multiply yours with a royalty rate. And that results again in a value of type euros. So now we can use these types that we added to our domain model in our calculation. So here is a more type-safe royalty calculation. So now we don't get a list of big decimal, but a list of euros, and we return a calculation of euros. So the rest of the implementation is mostly the same, just everywhere where a monetary value is defined, we use the euros type, and for the royalty rate, we use the royalty rate type. And now, if we run this computation, we will also see that our custom value formatters are used, which I can do in a minute, but also take into account that now with these stronger types, we can be sure that we don't confuse values that shouldn't actually be multiplied, for example. So in theory, if everything is a big decimal, for example, we could multiply euros with euros accidentally, and this is no longer possible now. So okay, let's run this calculation with Typesafe implementation of the royalties. And now you see that also our value formatters have been used. So here we see the royalty rate, 75%. We have proper formatting of euros, which also means that our labels for variables or expressions don't have to be so long anymore, because the information that it's euros is now part of the string representation of the actual value. Okay, so that's how you can add support for additional types to calclog. I also have a quick demonstration of integrating with third-party libraries. For example, there's already a really great library for doing calculations with quantities, which is squants. And here I have a short demonstration of that. I can calculate the daily sealed area in Germany. So I define a length in meters and a width in meters. And then I can calculate a soccer field area, which is the length times the width. And the daily sealed area is the soccer field area times 100. So here I'm turning the double value into a op literal. And then I'm turning the daily sealed area into hectares. So I'm showing you in a minute how I implemented this integration with squants, but let's first run this. Okay, so this is our result. Calculating daily sealed area, calculating soccer field area, and we see that the values are also properly formatted, which is basically provided by the squants library. This is not what I did. And at the end, we have a daily sealed area in hectares. So we see that in Germany, 71.4 hectares are sealed each single day. Okay, now one final thing I want to show you is how you can use different calculation description formatters. Or maybe I should first, show you the squants integration, actually. I think I still have a few minutes. So here, the squants library has this quantity type, and I'm defining instances of plus, minus, times, divide, and so on for any type that extends the quantity type. And I also provide an extension method for quantities of A. So if I have a calculation of A, where A is a quantity of A, then I can convert that value to a different type, or to a different measurement unit. So unit of measure is also a type provided by squants. So this is how I could do this as part of my calclog calculation. Okay, so the last thing, as I already mentioned, is that I want to use different calculation description formatters. So here we use a default formatter, which generates this string representation also as a tree output, but maybe we want something different. So you can implement your own calculation description formatter, but as an example, I have implemented a flat one. So let's see here what the difference is. Oh, I need to say using, of course. Okay, now we can run this calculation. So what this flat description formatter does is it first prints out all the input variables, which is the minimum SelfPub share per book, the number of sales, the royalty rate, and the total revenue. And then we have the calculation steps like this. So minimum SelfPub share is minimum SelfPub share per book times number of sales, which is 80 euro cents times 3, which is $2.40. And we do that for every step. And then we have the last step here. So in some cases, maybe some stakeholders find this representation more readable than the tree structure. But of course, you could also do something completely different and create an HTML representation or turn it into JSON using this calculation description formatter type class. Okay. So that's it for the demonstration. Let's get back to the slides. So here's my summary. There are a few options for creating an audit log of business critical calculations. And the simple logging approach is usually not sufficient. Tree log is a great choice if you have an experienced team which knows a bit about category theory and is not afraid of using monad transformers. And maybe they also just love using monads even for logging. And calclog is an alternative approach to that, which ensures that your audit log is really consistent with your calculation. Because calclog really derives the log from the calculation. It does involve some ceremony to add support for your own types and maybe for operators that are not yet built into the library. But yeah, if you don't want a monadic API for this kind of stuff, then this is what you get. And it's also really flexible regarding formatting or serialization. I must say that there is another approach that is probably worth exploring, which I haven't done with calclog, which is to use macros. Because right now, as you saw in the code, I have to give explicit names to the variables and when I create a binding. And maybe an alternative approach would be that you have a macro that knows how to describe a calculation at compile time. All right. That's it from my side. Thank you very much for listening to me. And if you have any questions, I will be available now in the Q&A.
Hi, Daniel. Thank you so much for your presentation today. All right, we have a few questions, so let's jump on in.
All right.
Since calculations are often run many times, can you say something about the performance of calclog compared to other solutions?
Not really. So in these use cases where we needed that, we never really had the requirement that this needs to be very performant, so we never measured this. But this is true in both the projects where we used this calclog approach and also where we used treelog. So unfortunately, I don't have any performance comparisons here. But of course, with treelog, which uses monad transformers, you could also say that it's probably not as fast as it could be without that.
Right. Thank you. Our next question says, this is a bit of a digression, but what does daily sealed area mean?
Okay. So this just means that the area of our land, which turns into highways or buildings or whatever, which was previously grassland or forest, that's the sealed area. So when you seal an area, you turn nature into that. And yeah, the daily sealed area, it's just the amount of land, in this case in Germany, that gets sealed every day.
Okay, thank you. Would it be possible, maybe with a metaprogramming, to use the variable name as the literal or binding name, so you wouldn't have to type it twice?
Yeah, I'm not sure when that question was entered into the Q&A, because that's basically what I was hinting at with my last remark in the last summary slide. So I think, of course, it would be great if we could use macros to just interpret an expression at compile time, because there we already have a variable name in there. Yeah. So I think that should be possible, but so far I haven't done any experiments with following this approach.
Okay, thank you. It looks like that's all the questions we have at this time. Daniel,
All right.
I want to thank you once more for joining us, and I hope you get to enjoy the remaining bit of the conference and the rest of the day.
Yeah, definitely. Thank you.